Hey everyone, so this video is all about analyzing continuity algebraically. So in class today, you guys worked on analyzing continuity from the graph, and now we're going to look at it doing algebra instead. So what happens if we don't have that graph? So a function is continuous at x equals a if the limit from the left equals the limit from the right, which equals the function value at a. So we already kind of even talked about this. The left limit has to equal the right limit, which has to equal the function value. All right. The only time we don't have to worry about the left and the right limit, though, is when we're looking at the endpoints. So we don't need to check both sides. When looking at endpoints. So for example, if we were looking for the limit at a right here, it wouldn't make sense to look at the left limit. We would only have a right-sided limit and then a function value at a. And same goes for b over here. It wouldn't make sense to have a limit from the right because there is nothing from the right. However, we would have our left-sided limit and then the function value. Okay? This down here should look pretty familiar because we talked about a lot of it already. So we're going to do this super quick. But a jump discontinuity looks like this, right? And we know that the limit from the left does not equal the limit from the right. In the first video, I changed colors for you guys, and I kind of did a little bit more explanation there, but I kind of feel like you've got that other video you can look back to if you're really confused on it, so I'm not going to go into super much detail there. For the infinite discontinuity, we are going to look at this one a little closer. So over here, from the left, we're approaching positive infinity, and from the right, we're approaching positive infinity, which means the overall limit, as I'm going to call this c also, as x approaches c of h of x, does exist. It's infinity. But it doesn't equal the function value, h of c, because that's a vertical asymptote right there. But the same thing can happen if the overall limit doesn't actually exist. So when we look at this function right here, we can tell that the left limit is negative infinity and the right limit is positive infinity, which means we can actually say that the left limit doesn't equal the right limit. So when we have these infinite discontinuities, sometimes we might talk about the overall limit not equaling the function value, and sometimes we might just say that the left limit and the right limit don't equal each other, since one goes to negative infinity and one goes to positive infinity. Okay? Then we've got our removable discontinuity, which we talked a little bit about in class today anyway, but we know from a removable discontinuity that's just a hole, and we know that the overall limit exists, but it doesn't actually equal the function value. So the limit as x approaches c exists, but it does not equal f of c because it's actually filled in down here. And then we know for this oscillating discontinuity that the left limit and the right limit do not equal each other. Again, we've got a little bit more detail in that other video, and I feel like you can look back to that or ask me in class if you need any clarification on that, but I'd rather get to some of the problems that we have to actually do for this lesson, okay? So when we are checking for continuity, one of the big ideas here is that if we have a rational function, we are going to possibly have some discontinuities, all right? So we are going to want to check for infinite discontinuities, which means we're going to be looking for asymptotes. And then we can also look for removable discontinuities, which means we're looking for a hole. Okay, so if we've got f of x equals x plus 2 over x squared minus 4, well, hopefully by looking at that, you guys can tell me we can factor the bottom to be x plus 2, x minus 2. And those x plus 2's actually cancel each other, which means we can simplify f of x down to 1 over x minus 2. But what we need to be careful of is crossing off that x plus 2. That's actually what created a hole right there. All right, so we have at x equals 2, or I'm sorry, at x equals negative 2, we take the opposite of it, sorry. At x equals negative 2, we created a hole, so we have a removable discontinuity. By canceling those out, we removed it from the equation, right? It's a removable discontinuity. And then when we look here, now we've got this x minus 2 on the bottom, and that's what creates an asymptote, which means at x equals positive 2, we have an infinite discontinuity because we created an asymptote. Okay? So rational function, which, by the way, I know you guys already know this, but I'm going to write it anyway. Rational function means it's a fraction. So anytime you see that, that's when we're going to be looking for an infinite discontinuity or a removable discontinuity. Okay? Then the other big function that has discontinuities is a piecewise function. So in a piecewise function, the big thing we're going to be looking for is a jump, which means we have two pieces that don't connect. And you guys can identify that pretty quickly from a graph. So now we just have to do it algebraically. And then we can also be looking for holes here if there's potentially a rational function as one of our pieces. Okay? Oops, and a hole would actually be a removable discontinuity. So we're looking for a removable discontinuity, which would be a hole. Sorry, I wrote that backwards. So when we look here, we can see that we have a line for 3 minus x is for when x is less than or equal to 2. And then we have another line, x over 2 plus 1, for when x is greater than 2. So all we're going to do is we're actually going to take this value and we're going to plug it into both of these. Okay? So if I do that, I get 3 minus 2, which is 1. And if I plug 2 into my other one over here, 2 over 2 is 1 plus 1 gives me 2. And since those two do not equal each other, I can say then that at x equals 2, there's a jump. Because I know that I'm jumping from 1 to 2. That's all it is. All right, we don't have to graph it. We don't have to do anything else. We can just say that there's a jump. I'm sorry, you guys. I don't mean to be coughing during your video. Okay, so identify the location of potential discontinuities. So now we have to be able to look at a function and decide, are there going to be discontinuities? And then we have to decide whether there actually are or not. So for this very first one, you can look at it and you can see that this is a rational function. So we know that when we do rational functions, we're looking for either holes, which are removable discontinuities, or asymptotes, which means infinite discontinuities. So when we look at this one, we're going to take the denominator and we're going to set it equal to 0. So 2x plus 4 equals 0. And we're going to solve that and we get x equals negative 2. So for our potential discontinuities, there is potentially a discontinuity at x equals negative 2. We're thinking that it's going to be an infinite discontinuity because we're thinking it's going to be an asymptote. All right? So when we look at the algebraic analysis, we're actually going to look at it in 3 parts because we're going to be looking at the left limit. So the limit as x approaches negative 2 from the left of f of x. And then we're going to look at the limit as x approaches 2 from the right. And then lastly, we're going to be looking at the actual function value at 2. So this is the algebraic definition of continuity. These three values have to equal each other. So we're going to decide if they are. So the limit as x approaches -2 from the left means that we want to approach something from the left of -2, so we can kind of think of like -2.1 or something like that, right? Well, if we were to plug that in, then we'd have -2.1 squared over 2 times -2.1 plus 4. Well, either way, on the top, we're going to be getting a positive number because we're squaring it. And on the bottom, we're going to end up getting a a negative small number. Well, when we look at that then, the overall limit there is going to be -infinity. Okay? Then we're going to want to look at the limit as x approaches 2 from the right. So we're going to be thinking about plugging in, that should have a negative on there. Sorry, guys. Negative. So we're going to want to plug in something like maybe -1.9. Okay. On the top, either way, we still get a positive number. And now on the bottom, we get a positive small number. Well, a positive divided by a positive small number means we're going to be approaching infinity from the right. And then when I plug in f of, sorry, again, I dropped my negative sign, f of -2, if I plug that in, we know we get a problem there. And so that one actually does not exist, right? We can't actually plug it in. It's undefined, which means overall here, what's happening is there is actually a discontinuity at x equals 2. X equals -2. I'm sorry, I'm having major problems with that negative sign there. Okay, next one. We've got a piecewise function. So we should be able to tell by looking at the piecewise function that the potential discontinuity is going to be a jump, and it's going to be at wherever the break in our function is. So there's potentially a jump discontinuity at x equals 0. So we're going to do the same thing we just did. We're going to evaluate those three things. We're going to do the limit as x approaches 0 from the left. We're going to do the limit as x approaches 0 from the right. And then we're going to actually do the function value at 0. And again, we want these three things to equal each other. If they do, then there's no discontinuity. If they don't equal each other, that's how we know there's actually a discontinuity. So if I want to do x approaches 0 from the left, well, that means x is less than or equal to 0. That's going to be plugging it into the top function, which means if I plug that in there, I would get -7 over 2. So the limit from the left is -7 over 2. To get my limit from the right, I'm going to be plugging it into the bottom function, which means -0 plus 0 minus 2, so -2. And then if I want the function value at 0, I need to go where I'm equal to 0, which means, again, I'm going to go to the top function, and that is -7 over 2. When I look at these three values, however, they don't all equal each other, which means that for this function, there is a discontinuity